Okay, so this is the lesson on mass spring systems that the sub did on, so Grandpa O did on Thursday. So those of you that are on the band trip, you would have missed this as well. What we want to talk about is mass spring systems. And before I actually start doing the notes on here, I want you to go ahead a few pages. So this is on page 9 in your notes booklet, but if we go ahead to page 10, this kind of shows you what's going on. I used to have a video that I played, but the link to it actually doesn't work anymore. So a mass spring system, it's a mass on the end of a spring, and we're going to assume the spring itself has no mass, and it's on a frictionless surface, and that mass will display simple harmonic motion. We're always only talking about horizontal, and so there's some equilibrium position that the mass has, and then you can pull it out to its stretch position. So you've pulled it this way out to its stretch position, and then if you let go of it, it's going to, it'll go back to its equilibrium position. It'll keep going through the equilibrium position to its compressed position, then it'll turn around and come back out through its equilibrium position, and then of course it would actually continue back out to its fully stretched position, back through equilibrium to compressed, right, and so on, and it just goes back and forth like this. It just keeps going back and forth, and I'm just stopping. I've got the arrows in the middle there to illustrate that there's an equilibrium position that's passing through. But basically the spring is going back and forth and back and forth and back and forth. And if it's a frictionless surface, it will do that indefinitely until you stop it. Of course, we always have to deal with friction, so it's not actually going to do it indefinitely. It will stop, but for our purposes, we're talking about it doing it indefinitely. Just as a reminder, simple harmonic motion, we'll call that simple harmonic motion. Actually, hang on, I'm going to do a text box and write, because that's just a little easier. Okay, so there we go. Okay, so on Wednesday we talked about pendulums, and we introduced the concept of simple harmonic motion, or it's usually just called simple harmonic motion, SHM. It is oscillatory motion. Oscillatory motion. And oscillatory means it has a regular period. Okay. So it's oscillatory motion that adheres to Hooke's law. Okay. And Hooke's law says that the deformation of an object is proportional to the force causing the deformation. So that's Hooke's law of proportional. Okay, so that just means that when you pull a spring out to its fully stretched position, or compress it to its fully compressed position, then the amount of that it's deformed, the amount that it's moved from the equilibrium position, is proportional, directly proportional to the force that you've applied to get it there. Okay. Okay, so I need to go back to the pen, and I need to do it on this page. Okay. Okay, so the period of a mass spring system, or how much time it takes for one full oscillation, so that would be all the way, from all the way compressed, all the way stretched, and back to all the way compressed again. That is equal to T, for period, is equal to 2 pi times the square root of m over k. Okay, so T is period in seconds, m is mass in kilograms, and k is the spring constant in Newton meters. Remember, the spring constant, it's just a number that tells you how stiff a spring is. So the bigger the number, the stiffer the spring. Okay, a couple examples using that formula, or just one example using that formula. 125 gram mass is pulled 29.0 centimeters away from its equilibrium position on a spring with 128 Newton meter constant. Determine the period of the mass spring system. So mass is 125 grams. That's 0.125 kilograms. To determine period, right, we just need spring constant and mass. So we don't actually need x. That would be the variable x eventually, but we don't need that right now. Okay, so we just need k as well, which is 128 Newton meters. And we want to find period. So period is equal to 2 pi times the square root of m over k, which is equal to 2 pi times the square root of 0.125 kilograms divided by 128 Newton meters. So, and you can type that into your calculator exactly as you see it there. When a bracket will come up when you pull up the square root, and don't close it until you finish putting the 128 in. What you should get there is 0.196 seconds. Okay, and then just as a sideline, if you have to solve for m, okay, or for k, how we want to rearrange that. You have to start, this is the formula that you have, is t is equal to 2 pi times the square root of m over k. And before you can go anywhere, you need to get rid of that square root, which means you have to square everything to get rid of that square root. So what you end up with is t squared equals 4, because 2 squared, pi squared, times m over k. So then solving is just a matter of cross-multiplying and dividing. So if you want to get m by itself here, multiply both sides by k. So t squared times k divided by 4 pi squared. Okay, and that'll equal m. And for k, k is just going to be 4 pi squared m divided by t squared. Got the equal signs in there. But you should know how to rearrange that on your own as opposed to memorizing those. Okay, and so there's two other formulas that we can use when we're talking about a spring. There's the elastic potential energy of a spring, which you've already used that formula. We did that in the work and energy unit. So energy is equal to 1/2 times k times x squared, right, where k is the spring constant in Newton meters, and x is the displacement from the equilibrium position in meters. So that displacement from equilibrium, right, like this would be, if we were looking at this and this was our equilibrium, we went straight down there. Actually, sorry, I should do it in the middle of the mass here. Let's go undo. Equilibrium position goes down the middle of the mass, and then, so then this distance here, that would be x. That's your x distance there. Or from the other way around, with the compressed position, this distance here would be x. So x is how much you have either compressed it or stretched. Compress the spring or stretch the spring. That has to be in meters. It's usually given in centimeters, but we need it in meters. And then energy, of course, is in joules. So simple harmonic motion is a special type of oscillatory motion that adheres to Hooke's law. And so then specifically for a spring, right, so we set up here that Hooke's law says the deformation of an object is proportional to the force causing the deformation. There's actually a simple formula for that. Hooke's law says that F is equal to kx, so k times x, and you put a negative sign in front of the k. So F is the restoring force, it's in newtons, k is the spring constant, Newton meters, and x is the displacement from the equilibrium position. And the reason why this is negative is because, like, if you're pushing on a spring, so if you've got a spring compressed all the way up here like this, right, okay, and you're pushing on it to get it that way, the force that you're applying, that's your applied force, is to the left. The restoring force, though, Fs, and I'm going to put a little s on here because that's the way it is in your formula sheet. So the restoring force, Fs, is in the opposite direction as the applied force. Like, or the way you can think about it is that the restoring force is in the opposite direction as the displacement for the equilibrium position. But if you had if you had pulled a string out, then there's your F applied, right? And that's your X then, of course, too, right? So that would be the displacement. The restoring force is this way. So because the restoring force and the displacement are in opposite directions, that's why we have a negative sign on the formula. Okay, so to actually kind of look at what's going on with the mass spring system, it helps to look at what the forces are, what the energy is, what the velocity is, what the acceleration is at each of the positions, right? At equilibrium position as compared to the stretch position and as compared to the compressed position. So we're just going to look at this now. And there's two different situations, right? Like we can deal with forces and we can deal with energy in this. So I'm going to use a text box again because this will just be a little easier with a text box. So the mass and the spring begin at rest at equilibrium position. Okay, and I'm actually going to, like I have this line here carried through, but I'm going to put in an actual line here to take it down. So if we actually show a line going down here, and straight down there, so that's the equilibrium position. And I want to change that to be dashed, just to make it a little easier. Okay, so there's the line. So that's going down at the equilibrium position. And so whenever I talk about equilibrium position, it's when it sort of passes, it either starts on that line or it passes through that line, either going this way or that way, right, going to the left or going to the right. Okay, so the mass and the spring, they begin at the equilibrium position. So the mass and spring begin at the equilibrium position. And so at the equilibrium position, displacement, so x, and these should have vector symbols over them, but I can't do the vector symbol on this particular program. So the displacement at the equilibrium position is 0. And then there is also no restoring force, right? There's no restoring force acting on it, so the force is 0. It has no energy if it begins, and this is because it's beginning at rest. Okay, so if it's starting at rest. When it passes through the equilibrium position, some of these numbers change. So energy at this point is also equal to 0. So because it's beginning at rest, then it also has no velocity. So velocity equals 0. And because the restoring force is equal to 0, the other thing, that equals 0 here is acceleration, where it begins. This is going to be different for when it passes through the equilibrium position, but this is because it begins at rest. So when you stretch it, when you stretch out that spring, so what you've done now is you've stretched this spring. So the mass and spring are stretched to the maximum displacement. And maximum displacement is called amplitude. Okay? And it's usually signified with a capital A. Okay? So at that maximum displacement then, so now x is a positive maximum, right? Because it's to the right in this case. So this is to the maximum displacement to the right. So x would be a positive maximum. Which means if we, like, let's just remind us of our formulas here. So let me see if we can do this with the pens and then go back. Okay, so energy, potential energy is 1/2 kx squared. Kinetic energy is 1/2 mv squared. Spring force or restoring force, Fs, is negative kx. And net force is mass times acceleration. So, if our displacement is at a positive maximum, then that means two things when we're stretched out here. And that means that the restoring force, okay, so the restoring force is a maximum. Okay, but the restoring force is going to be a negative maximum because remember the restoring force is in the opposite direction as the displacement. So restoring force is a negative maximum, and potential energy, okay, it's also at a maximum. Okay, and that the positive or negative doesn't matter for energy because energy is a scalar. So then what that means then is if the restoring force is a maximum, let me make sure I'm still recording. Yeah, okay. If the restoring force is a maximum, whoops, okay, let's try this thing here. Okay. Okay, so if the restoring force is a maximum, and that means acceleration is a maximum. And because restoring force is negative, then acceleration is going to be negative. Okay, so acceleration is a negative maximum. Because as soon as you let go of this mass, it's going to accelerate back. It's going to accelerate back this way when you let go. So x is positive, but the acceleration is going to be negative because it's going to accelerate back towards the left in the opposite direction as the displacement is. Okay, so if acceleration is a negative maximum, then that and EP is at a max because x is at a max. What that then means is that EK is 0. There is no EK because there's no velocity, right? You're holding it to the right. So EK equals 0, which then means that velocity equals 0. Okay, at that point there. Okay. So it depends on, and like I'm doing this separately here in terms of forces and in terms of energy, because depending on the information you're given in the question, you're either going to use forces, so Fs equals F net, to analyze the situation, or you're going to use energy, mechanical energy before equals mechanical energy after. It really just depends on what's going on. Okay, so that is when it's at its stretched position. When you let go of it here and it accelerates back this way, then it passes back through the equilibrium position, except now it's moving. Now it's moving when it's at that equilibrium position. So instead of like up here, we had it wasn't moving, it was at rest, so it had no velocity. It's actually moving through its equilibrium position, so it's moving to the left. Okay? It's moving to the left through its equilibrium position. So if it's moving to the left through its equilibrium position, then that says a little bit about what's going on in terms of forces and in terms of energy. So the mass passes through the equilibrium position, moving left. So, in this case now, its displacement equals 0 because x is a measure of how far it's been pulled from its equilibrium position. So x is how far it is in the equilibrium position. So if it's at the equilibrium position, then it has no displacement. Okay. When it's at its equilibrium position, the restoring force is equal to 0. Okay? Because restoring force is F is equal to k times x, and if x is 0, then F has to be 0. And potential energy is also equal to 0 because the potential energy involves x as well. And so if x is 0, 1/2 k times x is going to be 0. So if the restoring force is 0, then that means your acceleration is also 0. But now, when it's passing through the equilibrium position, kinetic energy is at a maximum. So kinetic energy is as high as it can be. It's at its maximum value, which then means velocity is at a maximum. And the direction of velocity doesn't matter. It is at a maximum, and it's going to be to the left. then when after it's passed through its equilibrium position, it keeps going on its way left, right? It keeps going to its compressed position. Okay? And so now it's displaced, it has a displacement to the left, which means its displacement is negative, and when you let it go, it's going to accelerate to the right. It's just going to have a positive acceleration to the right when it's let go, or as soon as it starts to move back the other way. So then that just changes this information from what it was up in its stretched position. So that becomes a little bit different. So now what's going on is the mass and spring are compressed to the maximum displacement which is amplitude. And so x is equal to a negative maximum, right, 'cause it's all the way left. So now restoring force is a positive maximum. Right? Remember, restoring force and displacement are in the opposite direction. And potential energy, now because displacement is a maximum, then potential energy is also a maximum. And so then that means that acceleration is a positive maximum. But it does mean that kinetic energy is 0, which means the velocity is 0. And both of these, the restoring force and the acceleration being at a positive maximum, that's as soon as it turns around and starts to go the other way, right? It hits that compressed position, then it moves right away, and then that's what causes this to happen. Then it passes back again through its equilibrium position. So now it's going back through the equilibrium position, so it's traveling this way again, so it's moving to the right, which means it has a velocity moving it to the right. So the mass passes through the equilibrium position, moving right. So now, again, displacement is 0 because displacement is a measure of how far it is from the equilibrium position. So displacement is 0, which means that the restoring force has to be 0 because that's based solely on x, and that also then means that the potential energy has to equal 0. So if restoring force is 0, then that means acceleration is 0. And if potential energy is 0, then that actually means that kinetic energy is at a maximum. And if kinetic energy is at a maximum, then that means that the velocity is also at a maximum, and that's to the right. So when you have, there's a few things to recognize from here. Okay. If you have a maximum displacement, so if x is a maximum, finish writing that word. It's not easy to write with the mouse. If you have a maximum displacement, then it's all EP when we're talking about energy. If you have a maximum velocity, then that means all EK. So at its maximum compressed position, this would be all EP. At its maximum stretch position, this would be all EP. And as it's going through the equilibrium positions, that's all EK. At any point in between, so if you were given, you wanted to find what was going on at this position here, then this would be EP plus EK. So it's just like a rock falling from a cliff. It has all EP when it falls off the cliff. It has all EK just before it hits the ground, and at any point in between, it's a combination of both. It's the same analysis. Okay. So, the displacement of the mass spring system is constantly changing, therefore the restoring force, the acceleration, and the velocity are also constantly changing. Energy, however, is always conserved. And then a couple things to remember here. Amplitude is maximum displacement of the mass from the equilibrium position, and that relates to potential energy and restoring force. I'll go back and change the size of my pen. And maximum velocity is the speed of the mass as it passes through the equilibrium position, and that relates to EK. And at any point in between the maximums, you have potential and kinetic. Okay, so the two ways that you can analyze this, and remember the maximum displacement or amplitude is signified with a capital A. So there's two ways that you can analyze this. You can analyze it using forces. And if you think about just drawing a free body diagram, right? Like if you have you have it fully compressed or fully stretched, right? You have a mass. So this would be you have a mass and you might have a force acting this way on it. That would be your restoring force. Might act that way, or it might act the other way. So it always helps to draw that free body diagram. When we don't have friction, we're not dealing with friction, right? So the only force we have here is our restoring force, which is considered an applied force. So in terms of forces, what we have is that restoring force, or F net, equals Fs. Okay, and we're only ever deal with horizontal springs here, because if we dealt with vertical springs, it'd be a whole other aspect into that. We'd have gravity that we'd have to deal with, but we don't deal with horizontal or vertical springs. So what we have here is that mass times acceleration is equal to negative k x. Okay? And you can solve for anything there, right? You can solve for m, you can solve for a, you can solve for k, or you can solve for x. Okay? It just depends on what you're asked in the question. So if you're given a question that involves acceleration or asks for acceleration, then that means you're going to use forces. So if it says acceleration, I should write faster with the mouse. Acceleration means you have to use forces. Okay? There's no other way about that. Acceleration is forces, velocity is energy. That's the kind of the way to keep it straight here. So then in terms of energy, okay, mechanical energy is conserved. Okay, so because the system is isolated, which means there's no friction, that means no friction. I feel like a lot of time passes while I write with the mouse. And mechanical energy before equals mechanical energy after. Okay, and again, it's just like with falling rocks and people jumping off cliffs and things like that. When we did it in work and energy, it's EP plus EK before equals EP after plus EK after. And you have to look at what the question is asking. If it says, remember, if it says max displacement, so max x, which is amplitude, right? I probably should have used a text box for this. Then that means all EP. All EP equals 1/2 kx squared. If it says max velocity, then that means it's all EK. equals 1/2 mv squared. If it doesn't say maximum, then you might have potential plus kinetic. And so you have, because if we go back here, at any point in here, right, like there's a displacement that's less than the maximum displacement, so that means it's going to have displacement and velocity at the same time. So you'd have to have EP and dk. And we'll do an example that relates to that. So what you have here is 1/2 kx squared plus 1/2 mv squared equals 1/2 kx squared plus 1/2 mv squared. And then you cancel out any part of that, those formulas that you don't need. If it is max, right, if it says amplitude, then that would be EP max. And if it says maximum velocity, then that would be EK max. And then you have actually a really rather simple relationship here that's just 1/2 Ka squared. And you don't have to use the A if you don't want to. Just recognize that A means maximum x equals 1/2 mv squared. Okay, so we'll do some examples using this. I think I have 4 examples really to do. Okay, a 0.375 kilogram mass. It's on the end of a 47.5 Newton meter spring. Determine the maximum acceleration if the mass spring system is stretched 27 centimeters to the right from its equilibrium and released. Acceleration means we're dealing with forces. And so if we have pulled this to the right, okay, so this is the x is to the right. Right, so that means positive x if it's to the right, and that means that the restoring force is directed to the left. The restoring force goes that way. So we have F net equals Fs. So mass times acceleration equals negative kx. Acceleration, anyway, that's an A. Acceleration is equal to kx by negative kx over m. Okay, so negative 47.5 Newton meters times our x, which is 27 centimeters, so that's 0.27 meters. And that x is to the right, which means it's positive, right? So this is a positive x. And then that's divided by 0.375 kilograms. Okay, and that'll give you negative 34, which is 34 meters per second squared, to the left, because it's negative. And that makes sense because if it's stretched to the right, it's going to move to the left when you let go of it. So part B, determine the maximum displacements. We want to find A. If the mass spring system has an acceleration of 24 meters per second left. So now, if it has an acceleration to the left, so if this is the way it's accelerating to the left, its displacement again is going to be to the right. So F net equals Fs. Mass times acceleration equals negative kx, okay, or ka, right? X, put here A if we want, A, capital A, equals x, which is equal to mass times acceleration divided by negative k. So the mass was 0.3775 kilograms. And we have a negative acceleration because it's to the left. So I should have been putting my directional justifications here. I wasn't doing that. So 24, negative 24 meters per second squared divided by negative 47.5 Newton meters. And the only time you have to worry about directional justification is with the forces, right? Because when we're dealing with energy, energy is a scalar, so the directions don't matter. And if you solve for that, you should get 0.19 meters or 19 centimeters. And it's positive, which means it's to the right. Okay, so we'll do a couple energy examples so you can get the feeling of how you solve those. So we'll do a simple one with max and max, and then we'll do one that involves not having a maximum. Okay, a 12.5 kilogram mass is pulled to an amplitude. Okay, so this means max x. So amplitude, that's max x, so that means all EP. Okay. It's pulled to an amplitude of 29 centimeters away from its equilibrium position on a spring with 128 Newton meter constant. Determine its max velocity, so that would be all Ek as it passes through the equilibrium position. Okay, so we have mechanical energy before equals mechanical energy after. I'm actually going to undo this here. So mechanical energy before equals mechanical energy after. Okay. Okay, so we would have 1/2, 0.5 kx squared plus 0.5 mv squared. mv squared equals the same thing. And, you know, part of me wants the equal signs to line up. Okay. And then what we can do is we can, we don't need to have, we just need a maximum potential on one side, a maximum kinetic on the other, and it doesn't matter which one. And since I'm solving for velocity, I'll leave my velocity on the left-hand side and my amplitude on the right-hand side. So I'll cross out Ek after, and I'll cross out Ep before. Okay? And it, like the sides, it doesn't matter what sides of the equation you're on. That's kind of part of what's going on here, so it really just doesn't matter. So then the other thing you can cross out is the halves. Right? The halves don't matter at all. So basically what you have is mv squared equals kx squared. And I guess I left out the EP plus Ek. Should put that in there. Before equals EP after plus Ek after. And the reason why it doesn't matter, like a couple of reasons why it doesn't matter which side you put which on is, first of all, mass spring system will keep going back and forth, back and forth, back and forth. So the before and after is sort of irrelevant. The other thing is an equal sign reads the same forwards as backwards. So this would be, didn't matter if you had kx squared equals mv squared. It means the same thing. So v is going to equal the square root of kx squared divided by m. So square root of 128 Newton meters times the maximum displacement, which is 29 centimeters, so 0.29 0.0 meters, and don't forget that that's squared, and divided by the mass, which was 12.5 kilograms. Okay, and also square rooting, so you should get 0.928 meters per second. Okay, most of the questions you're going to do are going to be like that, max EP and max EK. Example 4, however, is a little different. An object with a mass of 2.15 kilogram vibrates at the end of a horizontal spring. If the maximum speed of the object is 0.175 meters per second, what is the displacement of the object when its speed is somewhat less than that? So if we look at what we have here, like our mass would be like that, we could call this the equilibrium position. So let's call that equilibrium. And then this would be compressed. And this would be stretched. Okay. So remember here, this is EK, here, all EK. And at each of these positions here, it's all EP. Okay. Now, we're not interested in maximum EP. Okay, because we have maximum speed. So we have the center position here that we're interested in. We're not interested in max EP. We want to know, so like if this max EP would have some sort of displacement that we don't know. We at this position here, it has a velocity, a maximum velocity of 1.75 meters per second. Okay, and what we're asked to find is at some position in here, like maybe here, at this point here, it has a velocity of 0.975 meters per second. So we want to know what x goes with that velocity then, right? Because it's not a maximum displacement. Okay, it's not saying that. It's saying that if it has a displacement and a velocity at the same time, then it's not at a maximum. It's somewhere in the middle. So we still have our EM before equals EM after. Okay. So EP plus EK equals EP after plus EK after. Okay. And then what we have then is we have all maximum velocity on one side, and we have EP plus EK on the other side. So I'm going to pick the side, the way that I'm going to do this is I'm going to cross out the potential energy here. I'm going to keep my maximum kinetic energy on this side, because what I'm trying to do is solve for an x in this, and it's just nicer sometimes if I have it on the left-hand side. So 1/2 kx squared equals 1/2, or plus 1/2 mv squared. Equals 1/2 mv, and I could put a little m in there for max squared. Okay. And we're trying to find this. Okay. So the halves cancel. Okay. And we can have kx squared is equal to mv max squared minus mv squared. Okay, and then we're going to divide both sides by k. Okay, so then that cancels that k, and then square root both sides. So that cancels the square root. So we have x is equal to the square root of mass, which is 2.15 kilograms, times the max velocity, which was 1.75 meters per second, and that's squared, minus 2.15 kilograms, times 0.975 meters per second. And then that's all divided by the spring constant, which was 35.0 Newton meters. And just be really careful here. I would recommend solving for this whole thing, which means you need brackets around the top before you divide by 35, then taking the square root of it. and your x should be 0.360 meters. Okay, so if you haven't done so already, there's some practice problems here on page 14 to try. There are also a few workbook questions. There weren't many. There were only 3 in your workbook to try. So in your workbook on page on page sorry about my cough. Okay, page 220 to 221. Question numbers 14, 15, 16, and 17. So 14 to 17. And then there's a worksheet. That's going to be handed in. And you would have gotten that on Friday when you were there.